So we're going to try this. Oh, I need this. I'm going to try to talk loud today because with the mask on, I don't know how easy it's going to be for the recording to pick up the sound. So if I'm sounding obnoxious, that's why.
We have a chemistry group chat.
What's that?
There's a chemistry group chat. It's not.
Good. What does that have to do with what I just said?
Because if they don't get it, they just ask.
Oh, then you can help them out.
Exactly.
I love that.
Well, I'm usually
That's
the one
good.
asking for help, so they're not going to help for me.
So that's right, you can give back now. Awesome. All right, so let's see, we have been through quite a bit of this. We ended yesterday, well, with these two examples. Yesterday we spent some time focusing on bases. The fact that bases will result in hydroxide ion concentration going up. Find the pH of a base. You need to write a chemical equation for the base. That means water must be a reactant. And the rest of once you have the chemical equation written, where the base, remember the base's job is to accept a hydrogen ion. So water has to be the other reactant that offers up a hydrogen ion, and then the NH3 takes the hydrogen ion. So you can write what the products of that are. Find the pOH first, because when we solve for X in this case, X is going to be the hydroxide concentration. And then find the pOH, determine the pH from there. We did this one together in class, and then I asked you, I think we got through this yesterday, didn't we?
Yeah.
Did we do the methylamine? We did.
No.
May I ask you to take a moment and, having done this one as a base, try this one. You'll need a book because you need the Kb value for methylamine. So you don't have to all grab it. If you could just somebody and grabs one, and then the others around you can just look at your book, that would be fine.
What?
Thank you, guys.
A23?
A23.
We got one fucking like podcast.
Where are they?
Yeah, appendix 23. I believe the most difficult part of these problems is writing the chemical equation, figuring out what's happening in the solution, in the water, and writing a chemical equation. Once you can knock that out, the rest of it just flows. It just runs right along. Really? To the chemical equation? You have to. Because the methylamine there is a base, so it's got to take a hydrogen from something. So add water, yeah. Yes, ma'am. This is not the right key. You can just look up where's the
654 times
4.4 times 10.
Yes.
That's the key. Because this is a base, so you use its KB. Yeah, that's the hardest part. Now, this is a base. How do you know it's base? Because it's
Yeah, 2.2.
So,
Would that be the
job of the
pH?
base is to pull the hydrogen off of the water. It accepts the hydrogen. So, you got the water molecule there, good job. So the hydrogen is going to leave that and go on to the base. So that's going to make the base CH3NH3 with positive one charge. So it gains that hydrogen. So and the water, which has lost the hydrogen, is now just the hydroxide. So get rid of your hydrogen.
Materials
So it's going to be OH
Materials.
There's our chemical. Now you make the ice tea run. So yeah, the chemical equation has to look like this. Methylamine, CH3NH2, is a base, so it has to react with water because the job of a base is to accept a hydrogen ion. So the hydrogen comes off the water and goes onto that, so we get the CH3NH3 now, not just 2, but it has gained a hydrogen, and it's taken on a positive 1 charge because it didn't just gain a hydrogen atom, it gained a hydrogen ion. So the water has lost the hydrogen ion. The hydrogen left its electron behind. So we're left with the OH negative ion. So the OH negative is what we're going to be interested in because we need to find the pH of it. So this equilibrium amount is what we're after, the equilibrium amount of hydroxide. We'll use that to find the pOH and then change that to the pH. So yeah, our ice tables should be starting to look all pretty much the same. Well, that's plus X. Then the change was just minus X. So at equilibrium, it's 0.1 minus X, X, and then X. So the KB for methylamine, we just look up, is 4.4 times 10 to the negative 4. And that's equal to x squared over 0.1 minus x. Now, I will admit that this k value is on the border line between when you can use the 5% rule and when you can't. I will admit that when you get an answer for x using the 5% rule, it's going to be greater than 5%. It's like 6 point something percent. You saw that? So then you're like, shoot, now I have to use the quadratic formula. I would say that. Maybe some of you are like, ah, good, I get to use the quadratic formula. I don't say that. I will say this. The answer when you use the 5% rule and the answer when you use the quadratic formula are really close to each other. I can't remember now what the answer is. We did it yesterday in my other two classes. It's 0.006 something, right? 0.0064?
Oh, yeah. Oh, yeah.
Is that the
Yes.
quadratic formula answer?
Yeah, 6.4 times something.
Okay. So I want you to check this out. When we solve for x, which is the hydroxide concentration, with the quadratic formula, and I'm going to write that quad, we get 0.0064 molarity. If you just use the 5% rule, you get 0.0062 molarity. I think it's 0.0062. That's what you get. Look at how close these are to each other. Isn't this good enough?
Yes.
Is this worth going through all the trouble of the quadratic, distributing that term? This is not very hard because it's 0.1, but it's a pain. So I would propose this. I know it's called the 5% rule, but I propose that we change it to the 5, maybe 10% rule.
5 maybe.
Because look, I'm good with that. When I grade your tests and quizzes, there's a variety of answers I get because, as you go through a problem, you round differently or whatever, and I look at your work, and if your work is right, but your answer is slightly off mine, it's fine. And I'm good with that. So in the interest of just moving along in our chemistry and our lives, let's just use the 5% rule when it's remotely close. 5, maybe 10% rule. Raheem?
So if on a quiz or test, you can, like, it's right to use the 5% rule, like, you can, but you don't, will you be marked?
No, it'll be fine. That's fine if you use the quadratic. And
If you use the 5% rule, do you have to like justify or clarify or like say that you used the 5%?
just use it. The solutions manual goes nuts when the answers like outside of the 5% rule. They'll say assumption is horrible. We need to use the quadratic formula. I'm not so uptight about it.
It's like 7% of the Scottish rule. Not pretty much.
Yeah. Well,
5.1%
you'll
oh my
see.
God.
You'll see when you look at that solutions manual. They really don't like that.
5.1%. Oh my God. Unacceptable. You do 0 on tests.
Okay, so let's move on now. This is a good exercise too. Before we do that though, I'd like to take you, no, sorry. Let's take a look at this slide. Oh, if we just had this as our reading quiz and not the actual reading quiz, I bet we'd do much better, now that we've had the lesson. Are these compounds acidic, basic, or neutral? What about water? I think we all should get water right. And basic. Yes. It is neutral. Where are you? There it is. Water is neutral, of course, because when it dissociates, it gives off the same amount of hydrogen as hydroxide. Sodium chloride, what's that one?
Neutral.
That's also neutral. The sodium ion is neutral. The chloride ion is one of the conjugates of a strong acid. It's an anion of a strong acid. That's neutral. There it is. Sodium ion and chloride ion. Neither one of those are acidic nor basic, so it's a neutral. What about potassium nitrate?
Neutral.
Also neutral. Hey, Vishnu, you got a question?
Isn't water called like amphoteric or something?
Yeah, but not all amphoteric things are neutral. Like I showed you the example of HCO3 negative, it's not neutral. It's actually a base. Even though it can release a hydrogen, it will only release a hydrogen though if you put a base in there with it that's stronger than it. Then it'll give off its hydrogen. Otherwise, it'll be basic. Yeah. So just because something's amphoteric, that's the bottom line. Because something's amphoteric does not make it neutral. Water is in this case, but not all of the amphoteric things are. What did we decide about potassium nitrate? That's also neutral, right? The potassium ion, group 1 ions are always neutral. Nitrate ion is an anion of a strong acid. So that's neutral. What about NaNO2? Na is neutral, but the NO2 is a base. Yes, it's an anion, it's not an anion of a strong acid. So this is a basic compound. You put sodium nitrite into water, stick a pH meter in it, boom, up the pH goes. It's not huge, it's not a strong base, but it does go up above 7. Ammonium chloride. See what I'm talking about here with the amines and gaining a hydrogen. The ammonium ion, anytime you have a nitrogen cation that has an extra hydrogen on it, it'll be an acid. Yep, the chloride ion is neutral, and then the NH4 ion is acidic. In the interest of time, we have only just over 10 minutes left. If I had enough time, would do this exercise with you. I'm going to put this one off until tomorrow. This is an important one to be able to do. There are homework exercises like this where you get a series of things. These are all either neutral or bases. And you're asked, okay, rank these in order of increasing base strength. Which one is the weakest base? Through which one is the strongest base? This is important to be able to do. But we're going to run out of time. So I think we have time to do both of these. So if you have, we're going to just go one step further. Rather than just saying, hey, sodium cyanide, is that an acid or a base? Now I'm going to say, sodium cyanide, you got a 0.1 molar solution of it, what would the pH be? You'll need your table in the appendix. Let's go through this one together, and then I'll have you try one. Like I said before, the worst thing about these is writing the chemical equation out. Once you have the chemical equation, it just flows. Like Raheem flows through the water.
No.
So sodium cyanide, acidic, basic, or neutral? It is basic because that cyanide ion. So when you write a chemical equation for this thing, don't include the sodium. Leave the sodium off. It's a spectator. The sodium has no part in this at all. It's neutral itself. It doesn't do anything. So the cyanide acting as a base should have its chemical equation look like that. Water has to be a reactant for a basic reaction. And so the cyanide ion is pulling a hydrogen off of the water to make HCN, and you get the OH ion. So since we know the initial concentration of the cyanide ions, we have an ice table that we can set up, and away we go. Can I give you 4 minutes? I'm going to give you until 10:19 to see if you can get an answer for this. We do find HCN as an acid. Does that help? See my hint over there? It's hard to read. No, that's the acid. The K is an acid type. The K is got your base. Always the opposite. K double. You got to, which we know that, but it's 10 to the 14. take 1 times 10 to the negative 4 divided by.
What's the amount of payment?
That gives you the
So we gotta find it.
Tell me. Bro, it's not like a circle.
Okay.
I'm gonna write it right now. So KW, which is 1.0 times 10 to the negative 14 equals KA yes, times KB of its conjugate base. Right. So if you need the KB of cyanide, you just take that number divided by the KB.
Bro, there's no CN.
You should have looked for it.
There's no HCN.
There is HCN, it's down low.
Why are you looking in KB if it's HCN?
But I looked in here and it's not. No, it isn't.
Well, for the.
Oh, yeah. We have 11.6. I got 9.1. I got 11.1. I don't need to
Definitely 5%.
You don't have your calculator?
I don't want to pull it out.
Oh, yeah, that's a lot of work.
I just finished setting up. I did the sulfur act. And that's
Is
the
it
end.
this?
Yeah, the pH.
Yeah.
Oh,
That's a K, that's a K and A.
oh yeah. I mean,
Yeah, 1.6 times 10 to the minus 5.
It's like inseparable.
That was the one where you had parts?
It's an inseparable differential equation.
What is that?
Like you and the x equals like x plus y.
We had like 10 questions. We had to write down the integral.
X equals 1.3 times 10 to the minus 3.
Look, when we first started the limit, then we had to solve everything to the whole way.
You got that right.
Oh,
We had this derivative.
That was,
pH.
Oh my god, that was this.
that was, we had to write everything down.
Limit at each
Yeah.
zero.
It's 10:19,
Or make them.
so I'm hoping that you were able to process through this much. So we can make an ice table, and the KB of this base, cyanide ion is a base, it's the conjugate base of HCN. We look at our KB table, we don't find the cyanide ion, but we do have the Ka of HCN. So because of the hint I gave you right here, Ka of an acid times Kb of its conjugate base equals the Kw value. So if we need the Kb of cyanide, we take Kw, 1 times 10 to the negative 14, divided by the Ka of HCN. That gives us something times 10 to the negative 5th. And that is within the acceptable range for using the 5% rule. So sulfur X gives us the hydroxide concentrations. This is one where you have to find hydroxide. We find hydroxide. That's the POH from that, and then change it over to pH. I heard you say 11.1. That's right. 11.10 is the pH.
Oh, because then you solve for X, you subtract from 14.
Yes. Right. Well, sulfur X has the
And then
hydroxide
you
concentration.
find the
negative
POH
log of-
and then you
Yeah.
subtract from 14.
Okay, one last one with 5 minutes left. Oh, you didn't see anything. Don't look at your screen either. If you do, it's fine. But like I said, in a lot of these problems, the worst thing about the whole problem is just writing the chemical equation, figuring out what's happening in the water. Is there an acid present, or is there a base present, and to write the chemical equation.
Are we doing the acid strain thing tomorrow with like the binary acid oxidable acid complex?
We did that already with our first reading quiz.
Oh yeah, we did.
Yep.
Oh.
I don't have it memorized.
5.6 times 10 to the minus. Oh, that's KJ. Because NH4 is something like yeah. But I found it out. It's 5%.
It's 10 to the minus 10.
Oh, yeah.
That's a teacher guidebook. Textbook.
Where is it? Oh, you know what? I'll get it for you in a moment.
Oh, okay.
I'm using it right now. If you are able to see the notes that I published for this, you see that I chose to use the chemical equation that included water as a reactant. Even though the water is not really needed, when you have an acid, I could have very well done NH4 plus yields NH3 plus H plus. No, that's plus. I chose to put the water in there, and then the water would be accepting the hydrogen that the NH4 gives off, so it would make that hydronium ion. Remember that hydronium is the same thing as H plus, just a different way of expressing it on paper. I do this not because I want you to write the chemical equation like that. You're welcome to write what I wrote in blue. I just did that so that you could see that that's another possibility for how to write the acid dissociation equation. If you saw this like on an AP exam, I don't want you to get uptight like, what's the water doing there? It's an acid. Just know that when the NH4 loses its hydrogen, that hydrogen gets taken in by water molecules. You can express it as H plus if you want to. So going through all this, you find the Ka on the Ka table, which is nice, 5.6 times 10 to the negative 10. And so you finally wind up at the end with a pH of 4.82. The ice table is this, and once you have the chemical equation written, everything pretty much falls into place. Yeah, you got x squared over 0.4 minus a negligible x. If you have questions about this, I'll take them tomorrow. We don't have very much to do tomorrow. We should have a pretty short period.